Okay, so the primary objective in Storm the Castle is to make a device capable of launching a projectile, which in most cases will be a ball. And I think like depending on the year, what kind of ball it will be different. So yeah, and your score will be calculated based off the target distance and whether the target was hit or not. And here are some videos of some students who took this event. All right. So now that you guys know what how the event works, let's get into how we're going to build the device. And the name of the device that you'll be creating is called a trebuchet. And historically, this device was used in the past as a battle machine in the Middle Ages that threw large stones and other projectiles at enemies. The trebuchet was especially preferred by militaries because of its great force and great accuracy. All right, let's go over some rules. Okay, there's a very important rule, which is the device dimension rule. And the launch device, stabling weights, counterweights, and all other device components all must fit inside a 65 centimeter side cube. So you can't make a huge device. And yeah, it's just to prevent people from creating a very big device. Yeah. And here are some setup rules. Uh, your launch area is going to be 1 meter by 1 meter, and your uh your triggering device must extend 75 centimeters away from the launch area so that it doesn't contribute significant energy to the launch. So you'll be triggering the device at least 1.75 meters away from your device. And the distance is measured from the front edge, so here, to uh the center of the 5 gallon bucket or like the just the target. It's not always a bucket, but yeah, that just the distance is just measured from here to the middle of the target. Okay. Now we have the energy rule. So the launch force must be entirely supplied by the gravitational potential energy from the supervisor provided falling counterweights. The device without the counterweight and projectile must not contribute energy to the launch. So basically what it's saying is that the energy that your projectile gets must be entirely supplied by a counterweight. So we'll get into that in a bit, but it has to be completely supplied by gravitational potential energy. Okay. Um, so here are some rules on the counterweights and projectiles. So the counterweights, uh it always okay, the counterweights like they they vary by competition and by year, but this is just an example. So there's gonna be a heavyweight and a lightweight, and you're gonna have different lengths of beams, so you can prepare 2 different beams for your trebuchet according to the weight. And there's going to be two different projectiles, which this is an example. I think this was 2021, but yeah, this is all like based off of 2021. And yeah, and there's going to be two projectiles, and you'll use two different projectiles and two different beams for two different counterweights. Okay, so here are some examples of trebuchet designs that you could use. The most common one would be the one on the left. And I also personally use this in the competition, and it's probably um, the most simple. And yeah, it's pretty, yeah. Let's talk about physics. Okay. Um, a trebuchet is a great device with great power and great accuracy. The most basic concept you will need to know for this competition is the energy rule. This is on the rule book, so if your device doesn't follow it, you'll probably be disqualified. The energy rule is basically when the potential energy of the counterweight, uh, this heavy object right here, is converted into the kinetic energy of the payload, which is just a fancy way of saying the projectile. And this kinetic energy ultimately supplies the payload uh, with the energy which launches it into the air. In more scientific terms, the energy of the falling counterweight is just converted into the energy, the motional energy of the projectile. Um, you will learn more about this in physics class um, when you learn about conservation of energy. Let's go over some basic parts of the trebuchet that are important. Okay, here are some factors to keep in mind while designing a trebuchet. So how long should the beam be? Where should the pivot point be on the beam? Sorry. How high off the ground should the pivot be? The pivot is just this thing, just like the thing in the middle of the beam. And how heavy should the counterweight and the payload be? All right. Now we will go over some more important physics concepts which are extremely important when coming to understanding why everything happens scientifically. Some concepts you will need to know are projectile motion and conservation of energy. If you don't know what conservation of energy is, it basically means energy just doesn't just go away. It is always converted into something that is uh, so that the total energy in a system doesn't change. Uh, you will need to use projectile equations to derive the position of the payload as a function of time before and after it leaves the sling. Okay. Uh, the okay. So here's an optimal uh trebuchet design. Okay. Anyways, so we'll be going over some tips that will definitely help when building your trebuchet so that you can achieve great accuracy and great distance. So the beam on the counterweight side makes 45 degrees with the vertical in the initial release position. So um yeah, so hopefully you can see my cursor here, but scientifically when this angle reads 45 degrees, this initial release point of the ball or like the projectile uh, is most optimal for achieving a great distance. So basically, if the ball gets released from the payload or like the sling at 45 degrees from the normal, then uh, that should give you an optimal uh, launch distance. Um, okay, here's another tip. So basically, this length on this longer side of the beam should roughly be 4 times longer than the shorter side of the beam. Yeah, pretty simple. Okay. Uh, another tip. Okay, the length of the sling should be uh equal to the length of the long arm of the beam. So, if you see this picture right here, it's just saying like this L2, the longer side of the beam should be the same length as the length of the sling, which would be like maybe like a string or something. And like the rotation of this would supply the energy of the projectile. So a counterweight that has a mass much greater than the mass of the payload. So the counterweight must be a lot heavier than than the ball. Uh yeah, so on the payload, which is just the ball, and the counterweight mass are set by Science Olympiad competitioners, and they will vary by year. All right, so when doing the competition, you will be required to uh submit a data log. So you'll be asked to well like submit something showing your records of your I guess like your tests. And here's like a sample where like uh this is a distance, and this is for like the long beam and the heavier ball, and this is for the short beam and the less heavy ball. Yeah, pretty straightforward. So there's just different attempts. You just want to see like uh how you did whatever you did, or like just like your attempts, right? All right. That was kind of quick. Let's do a Kahoot. Give me 1 second. I'll paste it in the chat quickly. All right. I'm gonna post it in the chat right now. There's lots of people. I'll give one more minute for people to join. All right. I'll just be starting now. It looks like nobody's going to join. You can always join late if you want to join. I think like the pins are going to be there. For live. Oh wow. Okay, cool. Good job, guys. Oh my God, why is it so laggy? Is it laggy for you guys? Okay. All right. I'll go over this one. Okay, so the launch force must be only supplied by gravitational potential energy from the counterweight. So what that means is that the counterweight is there to supply the energy for the launch. So when you drop the counterweight, its its gravitational potential energy is going to be converted to kinetic energy, which is basically like the motional energy of uh for the ball. So when the counterweight drops, the all that energy is going to be converted to the ball's motional energy, which is just another way to say kinetic energy. Uh, and yeah, so that's what it means here. And uh, the dev the device without counterweight and projectiles cannot contribute to the launch. Um, so yeah, so this just means that uh your the energy that comes from the energy for the kinetic energy for the ball cannot be supplied by anything besides the counterweight. So yeah, uh I hope that makes sense. Okay. Um all right. There's another word for projectile. It should be easy. Somebody AFK. All right, good job, guys. Um, I don't think I need to explain this one. Good job, Jason. My name's Jason too. Oh my God, I'm so laggy. Good job, guys. Be straightforward. Wow, Jason. You're really on fine. Okay, cool. What is a kilometer? What is the optimal ratio between the long side of the arm and the short side of the arm? Okay, well, 3-to-1 works too. Yeah. 2-to-1 is okay. Yeah, I don't, I may, like maybe this would work, but um, I don't think it's good because yeah, torque. So okay, if you think of it as like um okay, so there's something called torque, and if you think of this, my arm as a piece of wood, and uh let's say like there's like a pivot here, like a knob. Okay, and let's say like my arm is like it can rotate like this. And if you put a weight like on the edge, then it like supplied the most force, like compared to like if you put a weight like closer to the pivot. So that's just like a concept like it's a concept called torque. And like basically the longer the beam is, if you think of this as a beam now, the longer this beam is, and let's say like the weight is like a counterweight, and like the longer it is, the more uh force you will get from the counterweight. And well, it's just said that 4 to 1 is a good ratio. Yeah. Okay. Good job. What is a kilometer? This is very easy. Good job, guys. Which is not true. Which rule is not true? Maybe I should have given more time for this one. Wait. Yeah. Okay. Yeah. Well, this is just yeah, it's just 10 centimeters away, but yeah. Do I really need to explain this one? Okay. Well, yeah. Next question. Good job, Rara. You can set the counterweight to whatever mass you want as long as it hits the target. True or false? Oh, just blow the answer. What? All right. Are you guys trolling? No, it's not whatever mass you want. The Science Olympiad competition hosts will set a counterweight uh mass for you. So um yeah, you don't get infinite counterweight mass. It's yeah, okay. It's set by the rules. Okay, last question. Ideally, what should the difference between the longer side of the beam and the sling be? Okay, so what should the difference between this L2 and L3 be in this graph? The sling is like the string that's attaching the beam to the pivot. Okay, okay, maybe this kind of like confuses you, like because like it's not to scale, but um yeah, it should be around the same length, ideally. Uh, yeah, we'll stop spamming bread in the chat. Good job. What is a kilometer? Wow. Okay. Um, yeah, that's all I have for you guys. If you have any questions, speak up because I'm not looking at the chat right now. Does anybody have any questions?
Is it a break or class end?
I don't think there are any classes after me, so I think it's over. Yeah. Wait, I'll stop recording. Does anybody have any questions?